Good evening. This is a build your own study guide for ES1 Scientific Investigation. I'm going to try to fit everything you need to know on one piece of paper and follow along with me and write what I write and draw what I draw, and it'll help you get an A on the test. So one thing you need to know is steps of the scientific method, like making observations, stating the problem, doing background research, stating your hypothesis based on your research, doing your experiment, also known as collecting your data. Then you analyze your results, draw conclusions. In this stage, you need to be doing a graph of some kind. And then the last thing you do is communicate or share your results. So a very important thing for this particular test is going to be identifying independent variable and dependent variable. So let's remind ourselves what each of those means. In an experiment, your independent variable, that is the variable that you are manipulating. So it's called the manipulated variable. So a variable is anything that can change. In an experiment, you just want one thing to change, and your ambition should be to hold all other things constant. Your manipulated variable is the one that you're testing, and you're changing it up front. Often teachers will say IV is the variable that I change. And if I could spell, that would help. The IV is the variable I change up front at the beginning of the experiment. The dependent variable is the variable that might respond. It's sometimes called the response variable. You don't intentionally change this. You're seeing if it responds to the independent variable. Sometimes teachers will say the D in DV stands for the data that we measure at the end of the experiment. So independent variable is a variable I change. Dependent variable, the DV, is the data that we measure. And so based on a problem statement, you need to be able to identify the IV and the DV in an experiment. And it helps to be able to identify constants and control groups as well. So I'm going to do a couple of examples. My first example is going to be chocolate chip cookies. And the problem statement would be, if I bake cookies with whole wheat flour, will they be more dense? So to visualize this experiment, you're baking a few batches of cookies with different types of flour. And you're seeing at the end, you're measuring the density of all the cookies, and you're thinking that the whole wheat ones might be more dense than the others. So in this experiment, your IV is the type of flour, and your DV is the density of the cookies. You might have a chart that looks like this. You got whole wheat flour and all-purpose flour. You got at least 3 trials, because that's going to make your results more accurate or more valid, more trustworthy. I'm just going to make up some numbers here. Let's say it's 4, 6, 5 for whole wheat. And then you've got 5, 5, and 5 for all-purpose flour. And these are all densities. So that would be like grams per centimeter cubed as your units. And this column here would be for the average. So you got 3 trials and you calculate the average, add up these 3 numbers and divide them by 3. You're going to get 5. Add up these 3 numbers and divide them by 3, you're going to get 5. So with these numbers I made up, for the experiment, the density of the cookies were the same. So your hypothesis was not supported. You'd still have a graph. The graph would look something like this. You'd have the type of flour, whole wheat and all-purpose, on the x-axis. That's usually where your IV goes. And then on your y, you have your DV, and we decided that is density. Lots of things that you could keep constant here, including the temperature of the oven, the other ingredients like the amount of sugar and the type of chocolate chips, the kitchen that you're making them in, all sorts of stuff, but we'll just list a few. Your control group, in this case, I would say is the group that has all-purpose flour. That's kind of your most normal conditions, your regular flour that most people are using. And you could have several different experimental groups. I only had one experimental group, the whole wheat flour, but there could be other types of flour. I think there's coconut flour and other stuff that you could add, but this is a simple example of an experiment where we're identifying the different components. And I'm going to do another example now. And in this example, I'm going to have 3 lamps. Each one of those lamps is going to be a different color. And I got my sunflowers growing under the lamps. And every sunflower is in a pot because I'm conducting my experiment indoors. I'll give these guys little cords. So, red, blue, green, and a problem statement would be, will the color of light affect the growth of the plant? And affect is a clue for finding IV and DV because IV has an effect on DV. DV responds or is determined by IV. So in this example, the IV is the color of the light, and the DV is the growth of the plant. Let's say we're measuring that in centimeters. And likewise, you would have charts and graphs. So for this experiment, got height, that's our DV on the y-axis. And then on the x-axis, our IV is the different colors of light. And let's say the red plants grew a lot taller than the blue plants and the green plants, so we determined that red light does have an effect on the growth of the plant. In this experiment, you could have a control group, the one that's under natural conditions. That's going to be a sunflower grown in sunlight. And there's lots of fun things you can keep constant with plants, such as the soil, the water, the light intensity, like the wattage of the bulbs. Yeah. So those are 2 examples of finding IV and DV in a given experiment. So when we're doing science, we like to use SI units. SI stands for Système International. That's French for International System. And if we're measuring distance, we do it in meters. Meters abbreviated by M, and measured with either a tape measure or a meter stick. If we're doing volume, we do it in liters. And for that, we would do a graduated cylinder. For mass, we're going to use grams, and that's going to be G. And you can measure that with a triple beam balance or a digital scale. SI units for temperature is degrees Celsius, and for time it's seconds. And you'd measure degrees Celsius with a thermometer and time with a stopwatch. And in the United States, we use US customary units, and we're one of 3 countries that doesn't use the metric system in our day-to-day lives. But as a scientist, you always use the metric system. A couple more things about volume specifically. So volume kind of depends a bit if you're measuring a solid or a liquid, especially if your solid has a regular shape like this cube. There's a clear length, width, and height. Then to find volume, you can multiply all those together, and then you get your volume in centimeters cubed or meters cubed. If you're doing a liquid, then you do want to use a graduated cylinder, and the water in the graduated cylinder is always going to have a curve like this. This curve is called the meniscus. You want to have it on a table at eye level, and you read the bottom of the curve. Let's say for this example, it's at 10 milliliters. That's the volume of a liquid. But you can also use a graduated cylinder to find the volume of a irregular solid, like this rock that I just drew. If you dropped it into a graduated cylinder with a known volume, and then here's the same graduated cylinder, and the volume has risen to, let's say, 13 milliliters. So the volume of my pebble is 3 milliliters, which is equal to 3 centimeters cubed. 1 milliliter equals 1 centimeter cubed. They're just 2 different ways to measure volume. Volume is related to density. Density equals mass divided by volume. A cute way to remember that is to draw a heart and then put a line through it, and you get M over V. Density equals mass over volume. So in a sum problem, you might be given the mass of a substance. The mass of that substance, let's just say, is 10 grams. And then you're also given the volume, which might be 2 milliliters or 2 milliliters or 2 centimeters cubed. To find that density, we would have to divide 10 by 2, and we would get 5 grams per milliliter, or it could be grams per centimeter cubed, depending on the problem. When you're getting the mass of something, using a triple beam balance, you have to make sure that all the sliders are in their notches, and then you add up the 3 masses that are on each slider. So it's the 1s, the tens and the hundreds, and you want to make it so that the needle lines up with the line on the right side. You also have to consider if what you're trying to measure is inside of a container, you might have to, this is for finding mass, you might have to subtract the mass of the container. So in class, we were measuring the mass of a liquid inside of a graduated cylinder, and you had to take the mass of the empty container and subtract it from the mass of the liquid and the container. Let's see, what else do you need to know? Well, it would be helpful to know about metric conversion. When you're using the metric system, meters, liters, and grams are your base units. Do a little section here on metric conversion. And so your base units with no prefix is meters for distance, liters for volume, and grams for mass. Your prefixes are kilo, hecto, deca, I'm going to put unit in there for base unit, deci, centi, and milli. And there's a mnemonic phrase to help you remember that. King Henry doesn't usually drink chocolate milk. And that's for kilo, hecto, deca, unit, base unit, deci, centi, milli. A kilo is 1,000 base units. So a kilogram is 1,000 grams. A kiloliter is 1,000 liters. A kilometer or a kilometer is 1,000 meters. Hecto, that's 100 base units. Deca, that's 10 base units. So a decagram is 10 grams. Base units are just one base unit. There's no prefix. Deci is a prefix that means a tenth of a unit. Centi is 100th of a unit. So a centimeter is 100th of a meter. That means that there's 100 centimeters in a meter. And milli is 1,000th. So a millimeter is 1,000th of a meter, and there are 1,000 milligrams inside of 1 gram. So the way these problems often look is you're given a value with a certain prefix, like let's say you get 361 centimeters, and you're supposed to convert that to, I don't know, decameters. So you have to write out your mnemonic, the first letters. King Henry doesn't usually drink chocolate milk. Figure out where you're starting at the C and where you're trying to get the D for deca. The first D is for deca. You count how many spaces to move the decimal. That's 3 letters to the left. So 361.0, moving the decimal 1, 2, 3 spaces to the left. So it's 0.361. 0.361 decameters is the same distance as 361 centimeters. It's just measured differently. Like if you measure your height and you're 1.5 meters, you're also 150 centimeters. Your height's not changing, just the way that you're measuring it. So all these prefixes have a letter that's associated with them. So the prefix for the abbreviation for kilo is K, for hecto it's H, for deca it's DA, for deci it's D, centi it's C, milli it's M. Another thing you need to know for the test is the difference between qualitative data versus quantitative data. Qualitative is an observation that is non-numeric. And quantitative, with an N, is numeric observation. So there's 35 students on the field trip, that's a quantitative observation. The students on the field trip had fun, that's a qualitative observation. I'll do an example that I can draw. Here's a bucket, and it's going to have some golf balls in it. And there's 36 golf balls in the bucket. That's the quantity of golf balls. If the bucket is red, that is a quality of the bucket. It's non-numeric, so it's qualitative. You also need to know about different kinds of graphs, like the line graph, the bar graph, which can go two ways. The scatter plot. Scatter plot can have a positive trend or a negative trend. Positive relationship, negative relationship. You have to know about pie chart and how to read it. And so this would be like 40%, 15%, 10%, 25%, something like that. And then there's the histogram, which always shows frequency. And it's like a bar graph, but the bars are touching. The very last thing that I'm going to do for this study guide is scientific notation. Scientific notation is a convenient way to write very big numbers like 27 million, or very small numbers like 0.00000079. So for scientific notation, your format is a times 10 to the nth degree. A has to be a number between 1 and 10, and n has to be an integer. That means it has to be a whole number, no fractions, no decimals, no square roots. It's just 10 to the third, 10 to the negative fourth, something like that. So let's start with the very big number, 27 million. We want to write that in scientific notation. So we need to get a place where the decimal point can be, where the number would be between 1 and 10. So I identify that as 2.7 there, between the 2 and the 7. And in order to get it there, we had to move it 1, 2, 3, 4, 5, 6, 7 spaces. So 2.7 times 10 to the 7th is the same exact number as writing all the zeros out. With a very, very small number, there's 1, 2, 3, 4, 5, 6 zeros before the 79. 0.000000079. Similarly, we're identifying a place where the decimal could be moved, where the number would be between 1 and 10, so between the 7 and the 9. In order to get there, it had to move 1, 2, 3, 4, 5, 6, 7. So 7.9 times 10 to the 7th, except for this time, it's the negative 7th, because we have a very small number, and we're moving this decimal point to the left. You might be asked to do the reverse. You might be given a number in scientific notation, like 3.6 times 10 to the negative fourth, and you might be asked to put that in standard notation. So if you're given this problem, you take the decimal point and move it 4 spaces to the left. And so you get 0.00036 is the same number as 3.6 times 10 to the negative fourth. A positive example of that, 4.3 times 10 to the 45th, That's a lot of zeros to write. So it's the reason why we have scientific notation. That's the same number as 4, 3, and then 44 zeros. So am I going to write all those out? You get the point. You would have to have 44 zeros after the 43, and that would be the same number as 4.3 times 10 to the 45th. I'm going to lose track of all these zeros, so I'm not going to write them all. Have a great night. Get some sleep. Eat a good breakfast. See you soon.